should be able to apply the fundamental counting principle, use graphic organizers to count the total number of items in a sample space, use the fundamental counting principle. Has anyone ever seen any of these words before, like sample space? What does sample space mean? Could you describe it, Carl? Does anyone know, anyone else heard that term before, sample space? Sample space. If you studied probability before in an earlier year, so probability means, it's kind of like, what are the chances? What are the chances that when I look out the window, I'll see a green car? Right? What are the chances when if I played the Wheel of Fortune and I spun the wheel, that I would get a vowel, right? Like, there's sort of games of chance. Now, to answer that question, what are the chances that I would look out the window and see a green car? I'd have to have some historical data to help me answer that question. I would have had to have someone counting all the colors of cars maybe for the last week, and then be able to make an educated guess. Some experiments, or that's what we're going to call them in math class, experiments. Even walking out and looking out at the color of a car would be an experiment. But all experiments or all situations that I could study would have a sample space. A very simple sample space would be this. Sample space for tossing a coin. Right? If I just flipped a coin, has anyone ever done that with a buddy? Said, okay, who wants to go first? We flip a coin, and it comes, what are the choices that I have if a coin is flipped? If I'm asked, what side do I want to take? What happens when you flip a coin? What do you call those two sides? Heads and tails, right? So the coin can either land heads or tails. That's it. You know what this is? That's the sample space. Sample space for tossing a coin. So anything you study or anything you're trying to organize would have a sample space. What about rolling or tossing a die? That means one, like not a pair of die are called dice, pair of dice, but a die is just one cube, right? You roll it. What's the sample space of rolling a die? 1, 2, 3, 4, 5, 6. So that's just sample space. You're just listing all the possible outcomes. Okay, so that sample space, we're going to see that come up again. What else? Use the fundamental counting principle to solve problems. We're going to get into that today. Use permutations, combinations, binomial theorem. So I'm just going to concentrate on these today. Use the fundamental counting principle to count the total number of items in a sample space and to list the sample space, and then use the fundamental counting principle. Okay, so again, look at your vocabulary words. Remember, try and note those, and remember that you should be able to understand all of these before before you are ready to write a test in this unit. Maybe what I'll do right now, just quickly, does everyone know what an odd number is? What's an odd number? Yeah, 1, 3, 5. These are examples, right? And John said, an odd number doesn't divide by 2, correct? Does not divide by 2 evenly. I can divide it by 2, but I'll get a remainder, right? How about...
Same also like prime numbers?
You know, I'm going to have to add that one in. I forgot that one, Abdullah. How about this one? Odd numbers increase
by 2. Even though they don't divide by 2, they're 2 numbers apart, right? There's a distance of 2 between each odd number. Even numbers are 0, 2, 4, 6. An even number divides by 2 evenly. Divides by 2 evenly. They also increase by 2. Okay, so there's 2 numbers between each even number. I'm going to add prime number in there. What's a consonant? Consonants and vowels make up the English alphabet, right? So what are how many vowels are there? We say 5 unless you're told, unless there's special circumstances. We tend to regard Y as a consonant. So there are 5 vowels. We don't usually include Y. It would have to be a special circumstance and you would be told to include Y. So what are the vowels? Yep, A-E-I-O-U. So how many consonants are there? How about I give you this? There are 26 letters in the English alphabet. Now, you might be kind of thinking, why is she telling me this? Well, some of our questions are going to involve, counting all the vowels in a situation or counting all the consonants. So there are 21 consonants. And Y is regarded as a consonant. Okay? Let's talk about prime numbers because Abdullah had alerted me to, we should have included this one. We've got odd numbers, even numbers, and then there's something called a prime number. Does anyone know the definition of a prime number? Could you give me an example of a prime number? Give me an example.
I think like odd number.
An odd number?
It divides itself and 1.
Good, that's the definition. A prime number, now we have to be careful here, has exactly 2 factors. 1 and itself. So keep that in mind. It has exactly 2 factors. So give me an example of a prime number. 3? Joanna, could you give me one? Because 3 only has 2 numbers that divide evenly into it, right? 1 and 3. Give me an example of another number that only has 1 in itself that go into it. 7? So those are all odd numbers like you said, right, Abdullahi? Is every odd number prime?
No.
Because 9 is not prime. It's odd but not prime. 13, 19, 17, not 21 though. 21's not prime. 27, not prime. Is every prime number odd? We know not all numbers are prime. Is every prime number odd? Which number is even but prime? 2. Yeah. Because it only has 1 and itself that go into it. Okay, is 1 a prime number? Okay, the answer is no. Why? Yeah, a prime number has exactly 2 factors. One only has 1 factor, right? So note the number 1 is not prime. It only has 1 factor. Itself. So 1 and 2 are kind of interesting numbers, right? 1 is not prime because it doesn't have enough factors. 2 is prime even though it's even, but it would be the only even number that's prime. And not every odd number is prime either. There's lots of odd numbers that are not prime. 9, 15, 21, 27, 35, right? Okay, so let's get started. We were just talking at the beginning how, for anyone who came a little later, this is a type of math that's not pre-calculus because it doesn't lead to calculus. This leads to more math courses that you might see in computer science, like John was saying, or probability. So it's kind of a nice, I think, unit to end on because it'll help your brain settle down with all those other topics you learned. As I said prior, there's no graphing, there are no negative numbers. We're dealing with real numbers and groups of numbers in different situations. I'm trying to make sense of them. So we're going to talk about something called the fundamental counting principle, and a lot of times it's shortened to FCP, just so you know, because it's a lot to write down. So let's see example 1. Aria wears a similar outfit to school every day. She wears a t-shirt and a pair of pants. That's her uniform. If she has a choice of a red, white, or orange t-shirt, and her choice of pants is blue or green, use an organized system to show all possible outfits she could wear to school. Okay? So, we're gonna call the t-shirt. Okay, what t-shirts could she wear? Her choice of t-shirt, I'm just gonna shorten to red, white, or orange. Okay? Her choice of pants is what? Blue or green? She's got to wear one of each, right? She's got to wear a t-shirt, she's got to wear pants. What are all the possible outfits she could wear? Someone give me an example of a possible color combination. Red, blue. Red, green. Yeah, and then it would be WB, WG. See John's system? He's taking the color of the t-shirt, then linking it with the color of pants. And then my last set is going to be what? OB, OG? Okay, so does everyone agree? There are six possible outfits. Agree? So this is called, as long as you knew what R stood for and what B stood for, and what that the first letter stood for the color t-shirt, the second letter color of pants, this is what we call the sample space. And that kind of goes along with what we were doing over there before, right? We were rolling the die to get the sample space. Make sense? Okay, the fundamental counting principle is an efficient way to calculate the total number of different arrangements of certain objects, rather than individually listing them and counting them. Okay, so what we did here, this young lady had a choice of 3 colors of t-shirts, 2 colors of pants. It wasn't that big of a deal to list the 6 combinations. Agreed? But what if I gave you a choice of 15 colors of t-shirts and 10 colors of pants? John says 150 possible outfits. We're going to figure out how he knew that so quickly. But let's just say there were 150 ways she had a way of arranging her outfit. Would I ask you to do that manually, list all 150 ways? No. I wouldn't even be able to count all, to go through and make sure you had them all correctly. So in a lot of cases, in most cases, we're not interested in having you list each one of the items separately in a sample space. I'd only ask for a sample space if it was reasonable for you to list it, like 6 items, maybe 10, maybe 12, but I'm not gonna ask you to list 27 items, right, or 35 items. So in those cases, I don't want the exact all items in the sample space, I just want the number in the sample space. That's what the fundamental counting principle gives us, okay? So we're gonna learn the use of the FCP here. So, the fundamental counting principle is an efficient way to calculate the total number of different arrangements of a certain number of objects rather than individually listing them and then counting them. When the number of choices gets too large, we can use the fundamental counting principle to calculate the number of options, right? If we're just interested in how many there are. The FCP states that if one task can be performed in M ways and another in N ways, then the number that the two tasks together can be performed is M times N. Okay? Use the FCP to calculate the number of different outfits that Aria, from example 1, could wear to school. So now I'm not asking you to list them or individually. We're just going to see the number, okay? So this is how we're going to do it. It says the number of one task can be performed in M ways, the second task in N ways, and totally, if I multiply them together, I'm going to get the total number of different outfits that this young lady can wear. So the first task was the color of t-shirt, right? This was color of t-shirt. This was color of pants. Now, how many choices did she have for the color of t-shirt? 3. Color of pants was 2. That means there's 6 different outfits. Can be created. That's it. That's all I was asking for, right? How many? So when I said, what if she had 15 choices for t-shirt, 10 choices for pants? That's why John said 150, because 10 times 15 is 150. Okay? Now, this is going to save us a lot of time, but it's also a really efficient way. Because you can see how this would lead to problems that you might find in computer science, right? When you're trying to figure out how many ways, how many different possibilities there are for this group of numbers, and how many possibilities for this group of numbers or letters, when you want to find the total number of PIN words or passwords that could be created, right? Have you noticed that, maybe you guys are too young, but even just a few years ago, phone numbers just used to be 7 digits in Manitoba. Do you remember those days? Before you had to use the area code too? Then a few years ago they said you have to start using the area code, right? That's an example of them running out of phone numbers, right? So that's this type of math. When you start to run out, you have to make sure you have enough digits created to fit your population. That's why one of the reasons that very few passwords, they'll ask you for just 4 digits or letters, right? Usually it's 8, because 4 digits, it would be really easy to crack a code with 4 digits, right? But with 8 or 10 digits, especially if they start mixing up letters, numbers, and symbols, it's very hard for someone to crack your PIN code or PIN number, right? This is the type of math we're talking about. So you can see that I don't want you to list, in most cases, I don't want you to list every single combination individually. Sometimes we will, but most of the time our answers are going to be too large for you to do that. So this is the quick way. So let's try this one. Example 2. If there are 2 roads to get from Winnipeg to Neepawa, then 4 roads from Neepawa to Saskatoon, how many different routes could you take to drive from Winnipeg to Saskatoon if you must drive through Neepawa? Okay. So it says use a graphic organizer to list and count all the possible routes. So they do want us to list them sort of separately, and then we're going to use the quick way. So what do we have to do here? We have to go from Winnipeg. I'm going to kind of draw a picture first. To Neepawa, and then Saskatoon. And they said 2 roads to get from Winnipeg to Neepawa. Okay, so I'm going to call these, I'm going to call this road 1, number 1, and number 2. And then 4 roads to get from Neepawa to Saskatoon. So 1, 2, 3, 4. And this time I'm going to call them letters, just to kind of keep them separated. So I'm going to say A, B, C, D. How many different routes could you take to drive from Winnipeg to Saskatoon if you have to drive through Neepawa? So they're making sure that you drive through Neepawa. So just, if I wanted to list the whole sample space, the total possible list of ways that I could go, well, what's one way that I could go from Winnipeg to Saskatoon? Using ones for the roads connecting Winnipeg and Neepawa, and ABCD connecting Winnipeg to Saskatoon. What's one possible route? 1A. Okay, what's another possible route? 1B, 1C, 1D. And then the other is 2A, 2B, 2C, 2D. Agreed? And how many? 8 possible routes. Agreed? So that's listing, that's using a visual, and that's using a graphic organizer. This is my graphic organizer. It's a chart or a table. It could even be like a tree diagram if you wanted. That's what graphic organizer means. It basically means, just gonna, because you'll be asked that. That means a picture, a chart, table, etc. Something like that. It's showing all the possible outcomes. Now, using the fundamental accounting principle, we're going to verify our answer. So, how many routes do I, or how many legs of the journey? I have, 2 legs of the journey, right? I've got Winnipeg to Neepawa, and then I've got Neepawa to Saskatoon. How many routes did I have? Winnipeg, Neepawa? 2, 4, 8. 8 possible routes. So long way, visual, pictorial, kind of showing your work, and this is just the quick formula way. And this is what's called the fundamental accounting principle, just the quick formula way. Okay. So I'm going to stop there for a sec. I think I'm going to assign a couple questions in the textbook, and then we're going to see. Actually, you know what? We're going to go with, let's do the examples in the book too. Let's just take a look at page 273. We'll quickly do this, and then I'll give you a little bit of time to work, and then we'll go on, because I think you guys can all handle that, right? Okay? And let's read the first example, and we're going to cover up the answers. We're not going to look at their answers. So on page 273, very similar to what we just worked on in our little booklet, right? Susan has 3 different blouses, 4 different skirts. How many different combinations of blouses and skirts does she have? They're not asking you for sample space. They're not asking you to list the separate. So I always do this. I do my slashes, and that's because things are going to get a little more complicated, and writing the slashes down allows me to label them, right? Because sometimes labels are going to be important. So these are the blouses, skirt. So the slashes represent how many decisions she has to make. The numbers on each slash represent the number of choices she has. So she's got to make a decision what blouse to wear, what skirt to wear. How many blouses? She has a choice of 3. She has a choice of 4. She's got 12 different outfits. Okay. Mark wants to have a drink and a sandwich. Okay, so those are his choices. Drink and sandwich. Drink, sandwich. He can choose from coffee, pop, water, milk. So coffee, pop, water, milk. He's got a choice of 4. For sandwiches, he's got what? 1, 2, 3, 4, 5. There are 20 ways, 20 different lunch combos that he could create if he wanted to change things up every day. And of course, you could show all these too if you wanted to, right? List using S for salmon and C for coffee, or et cetera, et cetera. Okay, Ryan likes to order a drink and popcorn when he goes to the movie. He can select from 4 different movies. There are 3 different drinks and 2 different popcorn sizes. Combinations of movies, drinks, and sizes of popcorn. Well, 4 times 3 times 2. So that's the movie, the drink, and the popcorn. So 24 different possibilities. And then let's try the last one. The last one's a little bit different. It's the same thing, same fundamental accounting principle, except this time they're using a 5-symbol code. So we're not using articles of clothing or types of sandwich. So a company uses a 5-symbol code on each unit of its product. The code consists of 4 digits, the first of which is the number 7, followed by 1 letter. How many different codes are possible? Okay, let's see if we can understand this. It's got a 5-symbol code. So that means there's 5 slashes, 5 positions that we have to fill. The code consists of 4 digits, followed by 1 letter. Okay, so these are digits. And this is a letter. How many different codes are possible? Can you see how already this is a little more complex, right, in a way to think about? Let's do this first, the letter. How many choices of letters do I have? They didn't give any restrictions or anything, just said choose any letter. How many letters did we say are in the English alphabet? 26. So I have a choice of 26 here, right? And these are all multiplied. Now, for the digits, the code consists of 4 digits. The first has to be the number 7. Okay, I get no choice on the first digit, right? You don't get to choose that. There's absolutely no choice to be made. And here, it's not, I shouldn't say no choice. I'm implying it's prescribed as a 7. So in my list, they've kind of nicely listed all the digits here. I'll list them again. The digits are, when we were listing all the letters at the beginning of class, we said there's 26 English alphabet letters. I didn't talk about digits. How many 1-digit numbers are there? 10, right? Okay, there's 9, the digits 1 through 9 and the digit 0, so there are 10 digits. I'm going to go back and include these on your vocabulary page. So 10 digits in total. So the first number is a 7, so there's only 1 7 in the group, right? So you don't get a choice of 0, like you have no choice, but I'm not going to put a 0 there because 0 would just 0 everything out, right? So there's 1 7 to choose from. Okay, he's gone. Now there's no other restrictions, so these 3 sets of slashes can include any one of these. So I have a choice of 10, and again I can pick any 10. They said I can repeat, I guess, and I can pick any 10. So that's what, 1,000 times 26, 26,000? There are 26,000 different passwords that could be created with the regulations that they made, right? The first one has to be a 7, the last one is a letter. So I'm going to assign, we're going to take a little bit of time, maybe till break. I'm going to get you to do, try working on assignment 1. How about going up to number 10, 1 through 10? And then we're going to talk about factorial notation. So 1 through 10. But first I'm going to just, if we go back to here, you know, with our We talked about what a prime number was. We talked about what an odd and an even, and vowels and consonants. I'm just gonna add up to the top here, the digits. There are 10 single-digit numbers. Now this might come into play, okay? We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So there's 10 of these all together. They start with an even number, end with an odd. That means there are 1, 2, 3, 4, 5 even, 5 odd. 5 are even. That's 0, 2, 4, 6, and 8. 5 are odd. 1, 3, 5, 7, and 9. So even an even number of evens and odds. How many are prime? How many of these guys are prime?
Three.
1, 2, 3, 4. Aren't they? Okay, not prime, not prime. Yes, yes, no, yes, no, yes, no, no. 4 are prime. And that's the 2, the 3, the 5, and the 7. Just so you have all that laid out too, okay? 0 is even, or is regarded as even. Okay, all right, so get to work. Take a look at page 273, 1 through 10, and then we'll talk about these two. Like I say, it's a completely different type of math, so might take a little time for you guys to get kind of into thinking this way. It could be a really fun section though. And I just got these tests back this morning, so I don't have them marked yet. That's the hard thing, how many slashes you have. You doing okay?
So, for this one.
Yeah. If you have Thanks, Ralph.
I have a question here. This one, I get 9. I see
How many
8.
ways can the digits 5, 6, 3 be arranged?
I see 9.
How?
Because there is like 3.
There's 3. Good, that's the hard part. So how many choices do you have to put here in this first one?
3.
Yeah. Okay, one of the letters is used up. Then how many?
Oh, there is no repetition? There
No.
is? Oh, okay, so,
No, I don't think so. You just have these 3. So it would be 6.
but it says 9 here. It says
Says
8. So,
9?
oh, it says 6, I think.
Number 8, it should be 6.
Yeah,
What is
6.
it? Number 8. Yeah,
It's
6.
okay.
Okay. You guys sped through that. Give you another couple minutes. I'll just do another quick check around. You're done with me? Leaving none of them blank, just gives you the answer to every, so there's only 5 questions. One, two, three, four, five. There's 5 questions on the test. So that means you have 5 decisions to make. So that means 5 slots. Now, how many choices do you have for each question? Okay. 2 times 2 times 2 times 2 times 2.
Yeah. You know, efficiency is, you have 5. I think tuition should be just the 5, right? They can test it on 5.
So you have 5 decisions to make, right? So 5 questions.
Okay.
How many choices do you have for question number 1?
One.
You can either answer true or false.
Yeah.
2 choices. 2 choices for number 2. 3 choices for number 3. Okay?
And what about the 6 subjects? I know it's yeah, 10 cents,
Mhm.
5 cents. Do I
So for
multiply all of
order,
them? Yeah.
if
can be heads or tails. For a die, heads or tails. For a 6-sided die, it could be 1, 2, 3, 4, 5, 6, or 6. So you've got the quarter, the dime, and the dice for the die. How many choices do you have for this guy? How many choices for this guy? How many choices for this guy?
6.
Right?
Most people are done. There's a few people still working, but since almost everyone's done, let's just talk about. Any questions in particular that kind of bothered anyone or thought were kind of challenging, or you got the answer but weren't sure why? Number 4? Okay, let's talk about number 4. Number 3 is I find number 3 is always tricky too, but always ask yourself, I think I said to a couple people here, the hardest part for me is deciding how many slashes, right? The choices that go on top of the slashes are usually easy. Once you've established how many slashes, then that kind of makes the question a little more crystallized. Talk about number 3 first, John. So you ask yourself, you're taking a test that has 5 questions. So stop. How many decisions do you have to make on that test? No. You have 5 decisions to make. If you have 5 questions, 5 times you have to ask yourself, is the answer true or false? Agreed? Yeah. So there's 5 decisions you have to make. 5 questions require 5 decisions. This is question number 1, question number 2, question number 3, question number 4, question number 5. Each one of these questions requires you to read and then what? Decide on a choice of 2 answers, right? You've got a choice of 2 for question 1, for question 2, for question 3, for question 4, for question 5. There are 32 different ways you can answer the whole test. I want to stop here for a sec because this is kind of important. If I did this the long way, it would probably end up being something like a tree diagram. And you can see why I wouldn't ask you for this, because this is so, it takes so much space actually. But you would start with question 1, right? They're just asking you how many different ways could a student conceivably answer this test? Right or wrong? They're not saying the student's right or wrong. Question 1, I can answer either true or false, correct? If I answered true, I have question number 2 now. How can I answer that question? True or false? Even if I answered false, I have the next set of decisions I have to make is true or false, right? Then I have to do this twice more, right? It's either true or false, true or false, true or false, true or false. See what's happening here? I've got 3 more to go. You know how many endpoints I'm going to get? So, okay, I'll actually do it this time, just so it's going to be really a nightmare. Maybe I'll just do, I'll keep going down with this one because it's going to be, and then question number 4, I have true or false, and I got a whole other set of true or falses, right? And then question 5, I have true or false, true or false. So they're saying one of the ways I could answer would be true, 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 right? I could answer 5, I could answer true, 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 true. The next one I could do, another student might go true, 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 false, right? There are 32 different ways you can write these codes down, right? That's what that 32 means. You can see why I wouldn't ask you to do the sample space this time. It's too confusing, too long. All I'm saying is how many are there? Well, there's 32 different ways. But ask yourself, how many decisions do I have to make? 5 questions, 5 decisions. Each one of them has a true, false answer. Okay, same with this one.
It's a little more sophisticated even because we're not doing the same question 3 times. We've got a quarter, a dime, and a 6-sided die are tossed. How many results are possible? So now these aren't decisions, I guess these are, outcomes in a way. So how many things am I studying? I'm studying the quarter, the dime, and the die, right? Quarter, the dime, and the die. All right, how many possible choices are there when I toss the quarter? 2. The dime, 2. How many choices for the die? I did talk about that. 6. One cube is called a die. The pair of cubes is called dice, just so you know. Okay, so that's 24. Yeah. These are a little easier, right, when they're just an English question, when they don't involve like an experiment, right? Anything else on these guys? Number 8? Can't repeat. So I think this one is think of these as, you know those numbers that go up on your house, like an address number? Think of them, you've got those 3 physical objects in your hand. You've got the 5, the 6, and the 7. How many ways can you physically arrange them? So how many placeholders do I need? I need 3, right? This is my first digit, the second, and who goes in third? So initially I have a choice of 3, and then I use one of them up. I only have 2 numbers left, and then 1, so that gives 6. Okay, let's talk about 11 and 12, then I'll let you guys go for a little break, and then I'll get you back in, and we're going to talk about factorial notation. Notice this was a little bit interesting. This was the first time I think we had a physical number of objects and we used them up one by one, correct? Here, we weren't using anything up. This was just sort of theoretical. I can add choice of 2, choice of 2, choice of 2. Here I physically had objects I was using up. We're going to talk a little more about this. The patterning that develops is interesting, right? When I keep using one more up, the number of choices goes down by 1. That's a very special property. And number 10 does that too? Okay, good, that's good. 6 students in a speech class all have to give their speech on the same day. One of the students insists on being first. Okay, we're saying that student does get to go first. How many different ways are there to schedule the rest of the speeches? You're right. So how many students do I have? 6. Okay, so I have my little clipboard with 1, 2, 3, 4, 5, 6. Who goes first? Who goes second, third, fourth, fifth, and sixth? So whoever this person was, I guess they're really persuasive. Maybe it was Eileen. Eileen says, I have to go first. There's only one Eileen. She's going there. Okay? I've got the rest of the 5 students, right? And if it was just, maybe I threw all their names in a hat and I pulled one, I have a choice of 5. That student's up, and then you're right, then I have a choice of 4. Then 3, then 2, and in the end I don't really have a choice. There's only one student left, right? So that's going to be 120. There's 120 different ways I can organize those students. Okay. Do you want to talk about 11 and 12 or go for a break first? First or after? What do you want to do? Okay, let's talk about them. A 4-digit number has the following properties. The first digit is an even number greater than 3. The second is an odd number. The third is a multiple of 4. And the fourth could be any digit. How many combinations are possible? I wish they would have told me. I actually need another piece of info. I don't know if they're letting me repeat numbers, right? That's the only thing I don't know. So I'm going to make up the rules as I go along, and my answer might differ from the back because of that. A 4-digit number, that means I need 4 slots, right? Now, anytime they give me a piece of info, I label it to try and keep my thinking straight. The first digit is an even number greater than 3. So I'm just going to say even greater than 3. The second is an odd number. The third is a multiple of 4. And the fourth can be any digit. I'm assuming they're gonna let me repeat. I think I can repeat numbers, like use them again if I wanted to. So remember I kind of gave that little list of things. I'm gonna open up my little paper here with my notes on it. At the top of the page, we had all our little rules up here, okay? So I need an even number greater than 3. Okay, so how many even numbers are greater than 3? How many choices do we have? 4, 6, and 8, right? That would be 3, a choice of 3. Okay, and I'm going to actually write down could be 4, 6, or 8. Okay, could be odd number, 5 odd numbers, right? Okay, multiple of 4, 4 or 8, right? Any digit, I have 10 digits. So what do I have? 10 times 10 is 100, 300. 300 possible kind of passcodes or PIN numbers could be created. Agreed? Okay, we'll finish off with the license plate number. License plates, except for those vanity plates, license plates contain both digits and letters. Suppose a license plate contains 6 symbols. First 3 are letters, last 3 are numbers. So 1, 2, 3, 4, 5, 6. So these are all letters. And these are numbers. Or digits, I guess. Okay, so let's just do, the first 2 letters are vowels, so vowel, vowel. The third is a consonant. All 3 are odd, so odd, odd, odd. I'm going to give you a sec to figure this one out. And I think, again, we can read, they didn't say anything about not repeating, so that means I could have like A, L. And you'll need a calculator for this section again. So if you haven't been bringing your calculator, bring a calculator. It's a big number, right? Is it big? Okay, anyone give me an answer? Eileen, what did you get? Okay, okay, seems like there's agreement. So how many choices do I have for the first position? 5. And since they told me they couldn't repeat, it would be another 5, right? How many consonants are there? 21. And then odd numbers, I have 5, 5, 5. Okay. So the answer is what? 5 times 5 times 21 times 5 times 5 times 5. 65,625. Different possibilities. All right, that's it. Go for a break. Maybe come back about 5 after, and I'll introduce factorial notation. So if you are staying and don't want to leave, you can read a little bit about that.
which we are.